There's two special types of function that we need to know about and we need to work with at advanced higher level, and these are called odd and even functions. Now they've got a special formula and a special condition that each has to satisfy on its own, but one of the big reasons that we like them is that they can actually make our life a heck of a lot easier when it comes to sketching them. So these two key types of function that do exist make our life very useful when it comes to sketching, and it can be very useful just in general with some of the work that we do. So what I'm going to do here is I'm going to tell you the definition of each of them and prove it to you, and then a couple of examples of each of those function on their own. First one I want to talk about is even functions. Now an even function is any function which satisfies the condition f of negative x equals f of x for all values of x. So every single number that you put into it, if I take negative x, work it through the function, and I get the equivalent answer of what I would get for f of x, this is called an even function. The reason this one's so helpful to us is that any even function is symmetrical about the y-axis. So all we need to do is look at half the graph and then be able to reflect it across and use that in order to help us plot it. So this condition here is one that this equation here would have to satisfy to be an even function. Now to prove it, what we have to do is you start with the left hand side here and we want to somehow get to the right hand side. So if I'm looking to prove that that function is an even function, if I start by doing f of negative x, what I end up getting is negative x to the power of 4 take away 8 times negative x all squared plus 3. Now I've done that. Negative x to the power of 4 is the same as negative x squared squared again, and we know that negative x squared is just x squared. So that squared again would quite simply equal x to the power of 4. We then take away 8, and it's times negative x all squared. Well, any negative number squared is just positive, so it then be take away 8x squared plus 3. And lo and behold, that equals the original function f of x. So what that means is I've just shown you that this function here is an even function. It satisfies that condition that we want. So if I were to sketch this graph here, it would be symmetrical about the y-axis. The other type I mentioned earlier was odd functions. Now the condition for any odd functions to be satisfied is this: f of negative x is equal to negative f of x, and that's for all values of x that we can plug into the equation in the function itself. Now the good thing about this one is that this type of function has half-turn symmetry about the origin. So if I sketched half of this graph, I could then pin it down at the origin, turn it around 180 degrees, and I've got the full function there because it's symmetric about that. Now if I had a question that said prove f of x equals this as an odd function, I would do the exact same as what I did in the last one. I'd start with the f of negative x and I'd try and make sure I got to negative f of x. So if I did this one, I'd do f of negative x, that equals the negative x cubed take away 2 times negative x. Negative x cubed, well that is actually just negative x cubed all on its own. We've then got take away 2 times negative x. So you've got take away 2 times negative x, minus minus gives you a plus, so it's then plus 2x. Well, if I take out negative 1 as a common factor in both of those terms, I would get negative bracket x cubed minus 2x. And lo and behold, that x cubed minus 2x is the original function itself. So that then equals negative f of x. So there you go. I've proven that that function there is an odd function. It satisfies the condition that we're after from up here, f of negative x equals negative f of x. Now, these are two special types of function we've talked about there, but not every function falls into one of those categories. Sometimes we get functions that are neither odd nor even, so they've not got the same symmetrical properties as those two functions. And all that we need to do to prove if a function is neither odd nor even is that it doesn't satisfy one of these conditions. So again, for this one here, if it was to say what type of function is this or prove it's neither odd nor even, I would still start the same way I always start before. I'd still start with f of negative x. So for this one, I'd do f of negative x, that equals negative x squared, take away 3 times negative x plus 1. So negative x squared, that's x squared, it's a good start. We've then got negative 3 times negative x, two negatives together, gives you a positive, so it's then plus 3x plus 1. Now that there isn't equal to the original function f of x. I've got plus the x here, but it's actually minus the x in there. So it's not equal to that, it's not an even function. But it also is not equal to negative f of x. So what that means, it can't satisfy the even condition, it can't satisfy the odd condition, so we know then that it's neither even nor odd. It's neither the even or the odd function. Now, there's a little trick to this, to be honest with you, which you can do and look at the original function and tell whether it's neither even nor odd. If we were to look at this function and split it up on each part on its own, the x squared here, that would be an even function. If I did f of negative x and it was just x squared, I'd get negative x squared, which is x squared. So that would be f of negative x equals f of x. So I'd have the condition for an even function. If I then looked at just the negative 3x part on its own, and I did f of negative x, I would end up getting 3x. So f of negative x would equal negative f of x. So this one here would be an odd function. So I've got a combination of even and odd functions. Because of that combination, I get neither. It's not one single type of function the whole way through. So there's actually a little trick. If you're looking at it and you notice that and it asks you what type of function it is, you should know in your head it's neither odd nor even. It's then just a case of proving it by starting with f of negative x and realizing it doesn't satisfy either of the conditions we want. Even and odd functions are very useful to us. They're very useful in terms of being able to sketch the graphs of functions very quickly, very easily, and very efficiently, looking at the symmetry for them both. So our odd function, f of negative x equals negative f of x, it's got a half-turn symmetry about the origin. Even function, f of negative x equals f of x for all values of x. That one's symmetrical about the y-axis. If it's neither of those two, we've got to do a little bit more digging in order to be able to sketch it accurately, but that shouldn't be an issue either. We just don't have that symmetrical property, so it's not quite a given as easy as we can.